So thank you, Pension, and thanks to everyone for attending this symposium. What I want to do is, no, this is not going to work, is to talk about strongly correlated metals, where it's been the focus of our research over the years, but also from that, the route that we've taken to electronic topology, and along the way, introducing the themes for this VBFF project of extreme quantum materials. In preparing this talk, it struck me that the notion that condensed matter physics is experimentally driven physics is really true, first of all. And secondly, how much our own work has been influenced by, obviously, the experimental community in condensed matter physics, but also our friends who take us seriously and collaborating with us. And the hope is that we have something to offer in return, perhaps serving, coming up with some notions from the theory side that could guide, but most importantly, really seek dialogues with experiments. So that's really what the theme of this VBFF project. Now, Ming started her talk by proudly showing off her gadgets. I don't have any gadgets, a picture of gadgets to show, but I'm very proud to introduce my group, the graduate students and the postdocs. So we have a lot of fun in our group meetings and give and take, and so that's a good opportunity, I think, to express appreciation for the current members of the group, but also the several recent members of the group who have gone on to do great things, and theory collaborators represented in the symposia by Maya Verganieri, who will speak later today, and experimental collaborators represented by Silke Pasha, who's also speaking later today. But I also want to mention that there's a group of heroes who started, for example, the F electron, correlated electron physics, and I've had the opportunity, great fortune to interact and collaborate with several of these, and so with a great appreciation, I want to express my gratitude to Brian and Maple for coming to this symposium. Great. So from a theoretical point of view, we have a bunch of electrons. You can have a neat Hamiltonian describing the band structure of these electrons in a lattice environment, and we consider some interactions, the manifestation of electrostatic interactions. So the textbooks will tell us that let's do perturbation theory, because we know exactly the behavior of non-interacting electrons. And there are a variety of techniques, but the basic notion is that the starting point is the bare objects. Conduction electrons are the building blocks for the low energy physics that we care in condensed matter physics, along with other bare objects such as phonons. Now, strong correlation in this context means that the electrostatic interaction U reaches or exceeds the kinetic energy of electrons as characterized by the bandwidth. So what can happen? That's the question of this field. And the community as a whole is appreciating that when interactions become large, we don't have to stick to the bare electrons. We can work with intermediate objects such as localized spins, orbitals, and that turns out to be an advantage, because if you do perturbation theory in interactions, there are statements, for example, that quasi-particle, lambda quasi-particles must emerge. You cannot destroy them. So, but yeah, from the empirical side, one sees all the features of the breakdown of the quasi-particle picture, and so give some sense that this picture helps. And now, this is a very general perspective. At the end of the day, we need to look at the materials, and so there's fortunately there's no shortage of quantum materials that have strong correlations. There's no shortage of exotic, interesting at least, sometimes exotic phenomena from magnetism to superconductivity to topology. So one has to pick a vantage point. And we have been considering heavy fermions for a variety of reasons as a community, but from the theory perspective, the notion that you have a material in which the active electrons can be divided into categories with very different velocities, and then therefore there's a ratio of velocities, which if you form the right ratio is a small parameter, and small parameter is what we seek from theoretical perspective if we want to consider effects of interactions, for example, non-perturbatively. So that's one motivation. And so narrow it down from the generic model of electrons, bare electrons interacting with each other with a Coulomb interaction in a system like this. We have atomic physics, which tells us that the F electrons by themselves would form narrow and essentially a flat band if you don't consider interactions. And interactions mod localize these F electrons, and as a result, they manifest at the low energies as intermediate low energies as localized spins in the most in the simplest of the settings. Spins would do quantum magnetism, describing by a Hamiltonian like this. But there's also conduction electrons associated with the SPD orbitals and exchange interaction between the two species of spins of electrons. Now, a notion that has served as a platform to build intuitions about correlated electrons is the Kondo effect, where you have these localized spins and the conduction electron spins forming maximally entangled up, down, minus, down, up singlets, and following the scheme of Feynman, we can break the singlet and construct these composite fermions, which have the electron quantum numbers. And importantly, these composite fermions coming out of the Kondo type of correlation effects, they are very fragile. The quasi-particle weight, the overlap of such composite fermions with a bare electron is on the order of 10 to minus 3. And this very small quasi-particle weight, it's non-zero, but very small, being very small, underlies a lot of extreme responses that one sees associated with this kind of correlated electron systems. But also, if Z is already 10 to minus 3, maybe we have a hope of suppressing completely to 0, something that theoretically is impossible if you start to do the bare electrons as the degree of freedom and do perturbation theory. So one place where the experiment served as direct motivation was some inelastic neutral scattering experiments by Gabriel Apley and others, which motivated the question, what kind of quantum critical behavior from anti-ferromagnetic metal to paramagnetic metal would be in these kind of Kondo lattice systems. And so there's the Landau notion of spontaneous symmetry breaking as the anti-ferromagnetic order would encode. Suppressing that gives a usual Landau type of quantum critical behavior. But here there's also the Kondo singlet formation, and that leads to the suppression of that leads to an actual energy scale and actual degrees of freedoms in the critical behavior. So that allowed us, that's where our own efforts started to be able to set up this, to do concrete calculations to show that things like h power omega over kBt scaling could actually be understood, and some unusual values of the critical exponents, fractional exponents. We spent quite a bit of analytical and numerical methods to calculate that, and that give a fairly reasonable understanding of experimental data, which provides support for a picture like this, which in turn allows us to make a statement that there should be jump of the Fermi surface across a second order quantum phase transition, which is a fairly dramatic statement. That statement can only be sensible if the quasi-particle weights starting from 10 to minus 3 here actually goes to 0 at the quantum critical point, and then new type of excitations emerge. And so the Fermi surface change has been an engine for extensive experimental effort that perhaps Silke will mention in her talk. It also serves as a notion that connects these kind of quantum fluctuating electron systems with the Coulomb plates and other correlated materials. The loss of quasi-particle at quantum critical point is much harder to probe, and we'll probably be hearing from Dr. Nathanson later today about the most recent experiment on short noise on that. Now, I don't want to get into too much details, but when we start to think about magnetic order paramagnetic phases, large Fermi surface associated with the Kondo singular formation, small Fermi surface associated with destruction of the Kondo effect. It turns out that one could go beyond the usual Downiak axis to think about other axes in a zero temperature global phase diagram. And this kind of phase diagram actually is useful in thinking about the behavior of the actual materials, but also motivating further experiments in materials that could cover different corners. But the reason I'm showing this is because about 10 years ago, with Silke, we started to think about, how do you actually probe, how do you scan through these different phases on the phase diagram? And probably over some lunchtime discussions, we thought, maybe spin-orbit coupling could be a useful tuning parameter. And we actually had some models, and there was a considerable experimental efforts. But the thing which I want to emphasize here is that once one starts to ask the question, what direct role does spin-orbit coupling play in a phase diagram like this? One starts also to step back to say, hey, we haven't really considered spin-orbit coupling directly. Could spin-orbit coupling interplaying with correlations lead to a change or enriched phase diagram? And in particular, very naturally, what's the interplay between correlation and topology? So that leads to a question such as this. We know that in insulating settings, there's a famous integer quantum Hall effect that's described by the band structure, non-interacting theory already. And there's a fractional quantum Hall effect, which is entirely driven by strong correlations. In other words, it's a state that cannot exist no matter what you do with non-interacting electrons. So the question is, in metallic settings, where there's good reasons that one ends up with, say, Dirac or wire semi-metals, could there be analogous situation where you have these gapless electronic topological states that are entirely driven by strong correlation that cannot exist in the absence, cannot be adiabatically connected to non-interacting systems. So this was a good motivation, but from theoretical perspective, we decided to start small and make the question more concrete. Is there a model whose ground state is topologically trivial without Kondo effect, but it becomes topologically non-trivial with Kondo effect? That's just a fairly modest step objective that we set for ourselves in marching towards that goal. And so we identified a model. This was the thesis of Sarah Graffi working together with Xinhua Lai. We focused on sort of the hydrogen atom case of nodal states in 3D, which is the diamond lattice. Diamond lattice is a nice picture drawn by Sarah, but the point to illustrate is that you have A and B sublattice, and there's an inversion center, which is in the middle of the bond, and we can introduce potential and tune that potential that breaks the inversion symmetry. And so this is a non-interacting band structure, in the absence of the Kondo effect, genetically you have these symmetry protected wire nodes. Well, you have wire nodes that symmetry allows it, but genetically it's happening far away from the Fermi energy, and the F electrons being so strongly correlated for modern insulator. And in the end, it's a topological trivial ground state. But when a Kondo effect happens, Kondo effect is one of these interaction processes that produce low energy excitations, meaning that these excitations, these composite fermions, must be extremely close to the Fermi energy, which shows a filling that would have been a Kondo insulator, but the symmetry dictates that the gap cannot be open, and this is wild nodes associated with these Kondo-driven composite fermions. So that's interesting in a number of sense. One of that is that you have these wire nodes, but interaction is pinning the wire nodes to the Fermi energy, so there will be transport consequences. But also, the velocity is extremely reduced because the z quasi-particle weight is 10 to minus 3, mass enhancement is 10 to the 3. So the velocity is 3 orders of magnitude smaller than genetic electron type of scale, and it would show up in a specific heat versus temperature T cube in the prefactor, where the reduced velocity appears in the denominator, and this is raised to the 30 power. So if V star is reduced by 3 orders of magnitude, this prefactor is enhanced by 9 orders of magnitude. And it was great fortune for us that we were thinking about such things. Silke was on sabbatical at Rice, and they had this material 343 heavy fermion compound, which had all the non-symmorphic, etc. symmetry reasons for having the semi-metal behavior, and the specific heat showing T cube with a gigantic prefactor. So it's an extreme response. As it turned out, that if you put the nodes to be extremely close to the Fermi energy, you could have small, tiny Fermi pocket. And that means that because at the wire nodes, the Barry curvature diverges, you would have extremely large Barry curvature, values on the Fermi surface. So that should have topological consequences. I'm presenting this part of story completely backwards. It was in reality, Silke students, Sammy Disaba, showed up in one of the RCQM workshops in my office and said, well, I observed this. Well, I said it cannot be true. It took me 6 months to be convinced. But in fact, if you work backwards, it's actually very natural. If you have a Fermi curvature, which is very large on the Fermi surface, you should have topological consequence. And that's the spontaneous Hall response. So do I have how much time?
Sorry. Yeah. So you have it's actually 5 more minutes.
5 more minutes. Okay. So I just want to give a flavor of 3 threads, which are based on this correlation to topology route. One is designing wire Kondo semi-metal materials. So I mentioned to you what happens with a diamond lattice. It's very natural to ask what happens in genetic lattices. And so the proposition is that strong correlations produce emerging excitations which are ping at a low energy, and symmetry constraints, lattice symmetry constraints act on these to be such that we end up with correlated topological phases, and that could also be used as a materials design rule to get the correlated topological materials. So this is a part of Lei Chan's PhD thesis, working together with Chen and Seti. And indeed, symmetry says that in a lattice that we chose, one of the square nets, there should be nodal line nodes that are topological. And we indeed find that Kondo-driven states have such line nodes as illustrated here. They sit extremely close to the Fermi energy, and there can be experimental consequences which have been explored in one of the materials that we proposed. I'm not going to go through the flow chart, but this basis of using space group symmetry to the constraining excitations which are produced by very strong correlations. So the cooperation produces symmetry, and strong correlations serve as a flow chart to look at the material database. And we screen in this work, we screen out 3 materials, and we claim that we've expanded the toric wild Kondo type semi-metal materials base by 300%. And so that's one of the line of effort that we started, and we certainly would continue. The other is what connect to what I alluded to. If the quasi-particle weight is already 10 to minus 3, I should be able to destroy the quasi-particle weight completely by introducing some computation. And so this connects to the motivation of seeking gapless electronic topological states, which are entirely driven by strong correlations. And so this is the work by Hao-Yu Hu. I don't really have the time to get into details, except that there's a way to construct Kondo lattice models to lead to a quantum critical phase. The quantum criticality is manifested in the spectral function that I'm scanning through K. So each line is a given K spectral function, imaginary part of Green's function, plotted with respect to energy. And you can see very broad spectrum. That's a loss of quasi-particles, but there are peaks that you can trace out. And here is the momentum where symmetry dictates that there should be degeneracy if we're not interacting electrons. But here, the entire spectral function is lying on top of that. So we have more general reasons to understand the robustness, but understanding topological surface states, etc. But the proposition, as backed up by this concrete calculation, is that you can have metallic topological states with a complete loss of quasi-particles. And thread number 3 is to scale up the temperature. I've talked about the F electron systems, which serve as very good motivation. Maybe it's just 30 seconds, Pincher. And so the atomic physics already dictates that F electrons act as local moment. And now this is really, Ming has already essentially said these things. So the point is that if you think about Kagami lattice, we're very used to this destructive interference picture. And you just remove the zeros, you end up with this compact localized states. And so this, and we can generalize it to a proper construction, these compact molecular orbitals, essentially like compact localized states, but there are tails associated with it. And these are complete bases, which are orthogonal. So for all practical purposes, you can think of this blob as atomic orbital, except that's a molecular orbital. It really acts as F electron, analog of F electron orbital. So it's really we're coming back, and the orthogonal combinations form the dispersive bands. So again, we have flat wide bands, except that these are topological, so there's a twist associated with it. And we can do things like creating Kondo-driven low energy excitations that inherits the topology associated with the symmetry of the lattice. That kind of constellation allows Chandon to search out this material copper 124, which you've already heard quite a bit in the workshop from Jian Wei Huang's talk, and also allows us to put the correlation topology together using these objects as local moment couple hybridized. Topology dictates that these local moment must be hybridized with dispersive states. So in that sense, topology acts as quantum fluctuation, and you can kill the order and get to the enhanced quantum fluctuation regime, coming back to this h bar omega over kBt type of scaling, except now I don't have any F electrons. So these are d electron systems, the temperature scales are higher, and in that sense, the intuition we gain from studying heavy fermion physics could play out in these kind of d electron setting, except that this notion itself of scaling up scale is actually not new. It has been around in the community. What our contribution is to add the flat band into the mix to make it concrete, and this mapping is exact. So let me just summarize. I talked about how the route that got us to theoretically to the wild Kondo semi-metal, which has a defining characteristic that Kondo-driven wire nodes are pin near the Fermi energy. And I talk about three threats: symmetry-based material design, wire Kondo semi-metals within quantum critical phase or at a quantum critical point, and the new frontier of using d electron system that hosts flat bands as a extremely connected but topological setting, the localized and dispersal states which are hybridized. And that's these three threats are essentially at this point what this VBFF project on extreme quantum materials is. And what the project does is really allows us to hopefully interface with experiments, with materials, with properties measure, and certainly we hope to be motivated further to think very much beyond these particular three topics.
Yeah. Any questions, now? Yeah.
I have one question. So, why like dispersion still exists when the quasi particle weight is lost? How to define topological invariant for?
Yeah, that's a good question. So, so for example, a setting like this, I made a statement that instead of degeneracy of single particle states, it's an entire spectral function which is lying on top of each other. So it turns out that there are two things. One is that I cannot use symmetry to place constraint on block functions because block function is not very useful. But instead, we are able to formulate the symmetry constraints on the Green's functions. That's point number one. So that's why this on top of each other is just not just the result of microscopic calculation. There's symmetry reason for that. And then, as Maya talked about during the workshop, we recently are able to formulate Barry phases, not in terms of the adiabatic motion in the real zone of the block functions, but in terms of the eigenfunctions of the Green's functions. And as a result, one can, even for this kind of definition of nodal states, we found that there's a quantization of the Barry flux. And so that's the beginning of topology. You can think further about bulk boundary connection, etc. But it's an important question which I kept certainly kept me awake in the middle of the night. Just what's going on? How to justify that? Yeah.
Okay. Right.
I'm just looking at this two-channel Kondo lattice model. Can you elucidate the nature of the two channels again? I mean, I know what they are in the quantipolar Kondo effect, for example.
Yeah.
Or the magnetic two-channel Kondo effect, but I'm just wondering what they look like here.
Right. So I think I have a picture somewhere that makes the discussion easier, although I don't think I'm getting there. Maybe this is as close as to what I want to show. So Brian is asking, we know the picture of the two-channel Kondo effect. You have local moment that's coupled to two degenerate bands of conduction electrons. So each is spin 1/2. So in the usual Kondo effect, we only have one local moment species and one conduction electron band, so they can form a spin singlet. But now the local moment needs to form spin singlet with this band of conduction electrons simultaneously with the other band of conduction electrons, and that's not possible. So that's a frustrating situation. That's why quasi-particle, thermoliquid quasi-particle is destroyed, and it becomes a quantum critical phase. Now, but what are these objects? And so we did a material search in this project based on the notion, which is connected to the idea in the field that you can use the spins as channels, but use the orbitals as the local moment, something you spent a great deal of your career on, Brian. And so symmetry, lattice symmetry comes in two forms. One is on the symmetry based constraints on dispersion or degeneracy, which I talked about, but also lattice symmetry comes in the kind of low-lying F lecture levels that come into play. So we identify some non-Kramers doublets materials, and there. So this would be the effective spin 1/2 associated with the orbitals, and these arrows actually represent the orbital degrees freedoms of electrons, and the fact that there are two is protected by Kramers degeneracy.
Think about that. I mean, the quadrupolar Kondo effect is simple because it's a quadrupolar interaction, and real spin up and real spin down are the two degenerate bands.
Yeah. So that's at least the materials that we've thought about, and so far we identify 3 candidates are precisely like that. These two degenerate species are the spin up, spin down degree freedom, and the arrows are actually representing the orbitals. So these are pseudo strings.
Okay. I think that,
Recall that this Kondo wire, like for the topology insulator problem is the Fermi energy never cross the gap. It's not really insulating. But for the Kondo topology insulator, by definition, we have the lack Fermi energy always in this Kondo gap. Right? I'm asking for this wire symmetrical one. Do we have a lack always key the Fermi energy to the wire point?
Yeah, so that's let me just get back to the right slide for that issue. So what Binghai is asking is that in typical weakly correlated wire semi-metals, there's no particular reason that a node is sitting with the Fermi energy or even close to the Fermi energy, right? But in a Kondo insulator, so you might just think about this picture with these red lines wiped out in your brain. That would be a Kondo-driven gap, and because Kondo-driven states must happen within KBTK of the Fermi energy. If you have a gap, the gap is Fermi energy is crossing the middle of the gap. That's the usual Kondo insulator picture. Now here, for this diamond lattice, symmetry and with a small emerging symmetry breaking potential, symmetry dictates that this is not allowed. You cannot open this full gap. So as a result, you have these decorations, which are the actual states that must be gapless. And so it's almost like there's a restoration of particle hole symmetry in a problem that doesn't have particle hole symmetry. If the nodes are forced to develop and they are in the middle of this gap, there's a good chance that the nodes are happening precisely or very close to the Fermi energy. And that's precisely what happens in this model we studied.
can I ask you a question? Can you go to your hypothesis of this the orbital, the magnetic portion, the last portion, where the 3 form object?
Yeah.
So do you expect that to be actually a sort of a wave vector dependent, or this because in all of the Kagumi lattice magnetic irons, the low angle part is always a single object, meaning that if you look at the spin wave, like even the stuff that Robert Quinn showed, the spin wave can always be fitted like a simple Heisenberg line. Only the high energy part. Yeah, so I'm curious. So
I want to drive the system to the quantum fluctuating regime, but imagine that we're in the order state. And so following this route, it's this object which acts like the basis for the Heisenberg model. So this object produces the spin. It's very localized because of the relative flatness of the band. And so this acts as spin, and therefore the magnetic excitation should be of the form that's associated with local moment description. And being a local moment means a spin 1/2 degree of freedom that's associated with this distributed, spatially but locally distributed, not extensively distributed. So that's a notion of the compact. It's a molecular orbital. You have some orthogonal orbitals which don't do this, but this combination like in this case example, angular momentum ±3 that does this job. And so that can be tested. Like, if you measure this mode, if you can establish that this mode is associated with spin 1/2 Heisenberg-like degree freedom, that would be going, and with the form factor information, that would be one way to test this hypothesis. And there are other spatially local measurements. One could maybe STM. One should be able to zoom into different points of the lattice and see whether the distribution is like this.
Okay.
So can be tested.